Hey folks, in this video we'll be talking about Warburg circuit elements, specifically looking at the difference between an infinite and a finite Warburg element. This video is based off of our free 5-part EIS webinar series created by my colleague Dr. Neil Spinner. This video is broken up into several sections. We'll go over what is Warburg diffusion, what is a Warburg circuit element, and then the difference between an infinite and a finite Warburg. Lastly, we will go over some of the mathematics behind Warburg circuit elements. Timestamps are in the description below. And lastly, before we begin, please don't forget to like, comment, and subscribe.
Now, a Warburg element, some of you may be familiar with already or have some experience with this circuit element. And a Warburg is very broadly describing diffusion. So the impedance of, essentially, or the diffusion of an electroactive species around to or away from an electrochemical interface. And usually this is solid liquid because diffusion typically takes place in the gaseous phase, in the liquid phase, although sometimes it does take place in the gaseous phase as well. There are two types of Warburg elements, infinite and finite. And in the finite category, there's two further types. There's open and short. And there are as well, when it comes to the simplest sort of model where you add a Warburg element, when you look through the literature, you might see two similar circuit diagrams that are used, the one here and then one here. And I'm going to be using this one today, where you have the Warburg element essentially in series with the resistor. It's kind of in parallel with the capacitor, but you see this one as well in the literature. Most frequently this one occurs, and mathematically these are quite similar. There is some difference in terms of how the plots, for example, will look, but under a lot of sort of what I would call normal ranges of values for the resistors, capacitors, and the Warburg elements, if you put the plots side by side for both of these circuits, they tend to look quite similar. So to be honest, I'm not 100% certain what sorts of justification you might have to use one over the other. For example, is the diffusion in parallel with some capacitive process, or would you consider the diffusion to be in series with the whole charge transfer process? There's probably ways of discussing those, and there may be some more analysis in the literature, but for simplicity, I'm just going to assume this model. So the infinite Warburg diffusion element is the most common one. Typically you have a W, just a plain W. Usually when you see that, that means the infinite Warburg. As indicated by the name, when you consider diffusion to be infinite or semi-infinite from the electrode surface. So you have some kind of situation where you have an electrode, like a disc electrode or a plate electrode, with some characteristic length or dimension in, let's say, a solution or a glass cell with a large volume comparatively to the size of the electrode. Another way to think about this is that because we have molecules or ions or electroactive species diffusing, because the electroactive species is obviously very small, right? It's on the order of nanometers or something even smaller, that we have even a smallish volume of solution, diffusional path length can still be considered in many cases infinite or semi-infinite, just because of the distance that the molecule has to diffuse compared to its size and the size of the electrode. So essentially we have diffusion in this semi-infinite bulk solution, and the impedance associated with that. Once the species reaches the surface, we'll abbreviate it as A at the surface, where the electrode can now interact and reach this species. And then we have our Randall's sort of process, our charge transfer process. Let's say A goes to B and then B diffuses away. The impedance of this process and this circuit element, this expression here. And I mentioned that I prefer personally to have the W in the numerator. Sometimes you'll see it in the denominator. Sometimes you'll see sigma is a variable that people use for the Warburg. These are somewhat interchangeable. Obviously, the units will just be inverted if the constant is in the denominator, but I like it in the numerator because this equation, which is straight from Barden-Faulkner's textbook on electrochemistry that I'm sure many of you are somewhat familiar with, this expression for the Warburg constant can be used to get an estimate of the diffusion coefficient. And so that is the power through the theory of diffusion in this Warburg element, that we can get a real physical constant of our electroactive species. So we sort of conventionally neglect the species, B, which is not an appreciable concentration, and we focus on one of these. We can basically solve for the diffusion coefficient. We know the ideal gas constant, the temperature, the number of electrons transferred, Faraday's constant, the area, and the bulk concentration. So these are all knowns or constants. We can essentially solve for our diffusion coefficient. So this is one of the benefits and the power of using a Warburg element, is that we can get, as I said, a real constant or a real property of our system. The primary graphical feature, again, as many of you are probably aware, is this 45-degree line that goes off to infinity on the Nyquist plot, essentially, depending on how low your frequency is, essentially. And so all of the same kinds of analyses that I described last week that you can use specifically on the Nyquist plot to get estimates of some of the circuit parameters apply here, which is to say the high frequency intercept on the real axis is equivalent to that ohmic resistance. We have a semicircle, and the width of that semicircle, as you can estimate, of course, you can't get an exact value perhaps just with your eye, but you can certainly get an estimate that is equivalent to the charge transfer resistance. And then we have our Warburg element. And again, the main feature here is that it goes at a 45-degree angle with respect to the x-axis. The second kind of Warburg element, which again has two types, is the finite Warburg. And so the first we're going to look at is called the Warburg short. And so no longer do we have semi-infinite, as you can tell by the name, finite. We have a fixed length of diffusion. So the only difference primarily, it's still diffusion, but in this case now we have a fixed length through which that diffusional process is occurring instead of an infinite or semi-infinite length. Also, just a note on the name, as if things couldn't get confusing enough, the Warburg short is also sometimes called absorbing. So sometimes you'll see W sub S, sometimes W sub A for absorbing. And I have seen, just to make it even worse, in some places it'll be called open boundary, which is a decent explanation considering that the Warburg short is really, it's describing, again, there's a fixed diffusion length path, but it's like a the where it's diffusing through is a porous or absorbing boundary. Essentially, it's not like a fixed non-porous boundary. Essentially, the other kind of Warburg that I'm going to show after this is called Warburg open, and so we have open boundary. You can see the confusion in the term. Now we're using open to describe both sometimes. So just a note of caution about that. However, I will mention that, as you're going to see, graphically the plots of the Warburg short and the Warburg open look quite different, and it should be easy enough to understand if you're looking at graphs in a paper or a presentation and they're discussing a finite Warburg element, whether they're using the short or the open, just based on what the plot looks like. So again, this is diffusion to a surface, or the electroactive species reaches a surface and then it diffuses through the interface. And that interface has a fixed length. Mathematically, the impedance of a Warburg short takes this form. If you ignore this term here, you see that this is the same as the infinite Warburg. We have W over this square root of j omega, or j omega to the 0.5, same form, but now we have this additional term, which is the hyperbolic tangent of another constant b times that same square root of j omega. And this b constant is equivalent to delta over the square root of d. So the same kinds of analyses apply here, where I can get the diffusion coefficient from this w. And then the circuit fit spits out a b constant as well. I can plug in my diffusion coefficient and I can get an estimate for this delta. Now, what is delta? Well, delta is the diffusion layer thickness. That is the measure of the thickness of the diffusional path. And just to prove to you that this is mathematically consistent, you could think, well, if my diffusional path is really large, if delta is really large, or let's say delta is infinity or semi-infinite, then b is also infinity. And if b is infinity, we have the hyperbolic tangent of infinity. And the hyperbolic tangent of infinity is 1. So if we have a semi-infinite diffusional path length, this term goes away, and the impedance is just this part, which is the same as what I just showed you for the infinite Warburg. So mathematically, this makes sense. And I'll show you that graphically as well, but it's just a helpful kind of reminder of where this comes from, which is that this is related to the infinite Warburg as well, just in that way, that if I make my diffusion length infinite, then it should be the same as the previous one, and it is. Now, mathematically, when I solve this expression for the real and the imaginary components, and you separate them in the complex plane, you get this disgusting looking equation. So don't worry too much about it, because I'm just going to use it to prove a point in the same way that I did previously last week with respect to the Randall's element. If you recall, I discussed with some of the math and some of the direction of the electron flow at high and low frequency, what happens. So let's do the same thing with this very large equation and expression here for the Warburg short. So at high frequency, what we have is this exponential term, which gets very, very large, as you can imagine, with the exponential with the frequency in the exponent, essentially. So what happens is this gets very large, and this just goes away. This goes to unity. So at high frequency, the effect is that we're left with this term in the real component and this term in the imaginary component. And I didn't show this before, but you can take my word for it. That is the mathematics for the infinite Warburg. So at high frequency, essentially what we have is a Warburg short breaks down to essentially an infinite Warburg at high frequency. Now at low frequency, what happens as omega goes to essentially 0? Mathematically, this term goes away. You just have to take my word for it, goes to 0. And this term here simplifies to w times b. Now, these are constants, right? These are circuit fitted constants. So at low frequency, the impedance of a Warburg short becomes a circuit element with 0 imaginary impedance and only real impedance that is a constant and not dependent on frequency. Well, if you recall, what I just described is a resistor. That is to say, an element who has only a real impedance that is equivalent to a constant. So essentially, another way to think about this Warburg short is it's like a fluid circuit element that is something between an infinite Warburg and a resistor. And so graphically, this is what it looks like here. So it kind of looks like its own Randall's element. This whole semicircle is the Warburg short manifesting. So we have our ohmic or uncompensated resistance in our first semicircle, which is our charge transfer resistance. And then we have this Warburg short. So the higher frequencies, we have this 45-degree angle, just like with the infinite Warburg, because that's what it looks like at the higher frequencies. And then this curls down and it starts to reach a constant. Eventually it would hit, if I went to low enough frequency, for example, it would reach a 0 phase angle and it would reach the x-axis. And so what it actually is like its own Randall's element, and the constant, or the width of this sort of pseudo semicircle, is equivalent to w times b. That's like the resistor value of this Warburg short.
All right, folks, I hope that you enjoyed this video. If you have any questions, please leave them in the comment section. Again, this video is based off of a 5-part EIS webinar series. We frequently make webinars, and if you're interested in attending one of our webinars, go to pineresearch.com to register. You can also see upcoming webinars on our website. We also make posts on YouTube, as well as our other social media platforms such as Twitter or LinkedIn. So make sure to follow us to learn about upcoming webinars. All right. Again, don't forget to like and subscribe, and I'll see you soon.